Hi and welcome. Thank you so much for being here with the National Bicycle Dealers Association and Human Powered Solutions. We're really happy to have Mike Fritz here with us again to give us more information on the safe charging and storage of lithium-ion batteries. He has a huge wealth of knowledge, and we are really excited to have him so that we can learn more and be safer. So thank you, Mike, for being here. I'll throw it over to you.
Thank you, Rochelle, and thank you to everybody that's participating today. It's encouraging for us to know that people are interested in this topic because it certainly is an important topic, and we think being armed with the knowledge relative to lithium-ion batteries and their pros and cons is a good thing in the industry today. There have been issues associated with safety of lithium-ion batteries. We're trying to raise awareness of that and offer guidelines to bicycle retailers primarily at this point. Obviously, it needs to cascade down to e-bike customers as well. But this obviously is focused on e-bike retail environments, and we'd like to get into that. What I'd like to do today is I'm sort of segmenting this discussion into three chapters, if you will. The first chapter is a recap from the last webinar. Many of you may have participated in that webinar. I think it was last November sometime. And basically it was intended to offer guidelines relative to developing and implementing protocols and practices in your shop to mitigate the possible negative aspects of lithium-ion batteries. And we talked about that at some length. We've gotten some pretty good feedback on it. So my plan is to recap last seminar quickly. I don't want to go through it all again. If somebody's interested in seeing it from the beginning, it is available on YouTube. I don't have the exact link, but we can certainly provide that. But it does offer guidelines, it offers procedures and processes, if you will. But today, I just will recap that quickly. Then I thought what I would do is give you some insight into the feedback that we've gotten from that first webinar relative to this topic and what we're recommending regarding mitigating the potential hazards associated with lithium-ion batteries stored in your store. And then finally, it occurs to me that it would be informative to offer a little bit of insight into the technology behind e-bike batteries. These things really are fascinating devices in terms of the energy storage capacity that we have. And I think a deeper understanding as to how they work, how they're constructed, how they're designed, and what safety features are actually built into lithium-ion packs would be very informative. So without further ado, I'll get into the recap from the last webinar. Basically, we talked about the fact that lithium-ion battery chemistry is really a breakthrough that empowers us to do a lot of things. Clearly, lithium-ion batteries were developed initially to power handheld electronics, cell phones, laptop computers, Walkman, things of that nature, because they offer the ability to store a lot of energy in a very lightweight, compact package, which is a very desirable attribute for those products. And but the issue was the early lithium-ion batteries that were used in handheld electronics were what we call high energy density, and that they do store a lot of energy, but they were low power density. It was real important that you only take the energy out slowly. And in a handheld electronic device, that's not a problem. But then we tried transitioning that technology into powering electric vehicles. And we ran into some early problems because that low power density the low power density attribute of lithium-ion batteries came back to haunt us. When you try to take the energy from a low power pack out too quickly, you overheat the pack, and that can oftentimes have dramatic consequences, and that's what we're trying to avoid. But over the years, the battery industry has developed what we call high energy density, high power density battery packs, which means that we can extract energy fast enough from those cells without overstressing them to the point of failure. And that's been the breakthrough that's basically enabled electric vehicles. Teslas, Ford is coming out with the new F-150 Lightning. Those products would not be possible were it not for the fact that we have these high energy density, high power density lithium-ion batteries to power those devices. And the whole point is one, you can carry a lot of energy to cause your vehicle to go a long distance, and you can take that power out such that it'll have the torque to accelerate, to carry a heavy load, to climb a hill, et cetera, et cetera. So this truly is an amazing breakthrough in energy storage technology that has enabled us to transition into these cleaner forms of transportation. But these high capacity energy storage devices do carry risk. And we all appreciate the fact that if you were to flip a match into a bucket of gasoline, you'd have a pretty dramatic result. Well, the same is true with lithium-ion batteries. There's a lot of energy contained therein. And unless it's properly managed and properly stored, it can release spontaneously, causing a fire. And unfortunately, that's happened all too frequently. So what we're trying to do here is to address that propensity so that people are aware of it and can take appropriate measures. The good news is there's significant progress being made in the development of safe lithium-ion batteries that don't have this propensity to fail catastrophically. They're called solid-state lithium-ion batteries. They eliminate the key element, the key component of a lithium-ion cell that's flammable, and that's the electrolyte. They're working on replacing the liquid electrolyte that actually is the transfer medium for the ions that carry the electrons from the anode to the cathode with a solid-state material that accomplishes the same function. And it does look like this is going to be a win-win situation in that these solid-state batteries not only are safer and more stable, they can also carry more energy, which is even better. It would be great if we could have electric cars that could travel 1,000 miles or electric bikes that go 200 miles between a charge. So that work is ongoing. The unfortunate part about it is it's probably 5 to 7 years out before commercially available solid-state batteries will be available. So in the meantime, we have to be aware of the fact that occasionally, under certain circumstances, battery fires can occur, and we just need to be ready. In the retail environment, there's one overriding acknowledgement that I'd like everybody to take away from this talk, and that's the fact that the chances of fire in your shop are minuscule. They don't happen very often. But the consequences of a battery fire can be so catastrophic that it's worth the time and effort to take these relatively simple steps to mitigate the possible damage. With a few relatively easy, inexpensive steps, establishing policies within the store, you can mitigate the damage in the event a battery does fail, and which would otherwise cause a problem. These safety steps basically require several things. Appropriate equipment, we'll go through that. A comprehensive training for all shop employees so that they understand the procedures that you implement, make sure they follow them religiously, strict adherence to the established procedures, and an unwavering commitment on the part of management to make sure that all the shop employees, all of the people within your shop are paying the due respect necessary to this technology to ensure that there's not a problem. Required equipment. This is straightforward. We recommend that you have a fire-resistant cabinet in your shop. And I'll talk about this in a little bit more detail in the feedback section because, we've had some comments relative to storing batteries in this cabinet. We recommend that you obtain a wire-style battery charging rack. In other words, when batteries are being charged, they're placed on this charging rack. We recommend that you obtain chargers appropriate to the battery packs that you sell in the e-bikes that you sell. Zip tie those to the rack so that you've got the correct charger to charge the correct battery on a device such that if there's a problem, you can quickly react to it in a safe and effective manner. We recommend that you have a 32-gallon industrial trash can available, about 7/8 filled with water. And I'll explain the rationale behind this in just a few minutes. We recommend a smoke detector. Clearly, one of the rules that we'll talk about in a few minutes is the fact that you never charge batteries unattended. There's always somebody in attendance when one of those packs is on a charger. But in the event that a pack fails while the shop is closed, you need to have a smoke detector to alert the fire department that in fact there's a problem going down so that they can react in an appropriate fashion. Plus, this can be an early warning for the shop even when it is open. One or more Class A, B, and C fire extinguishers. This is not to try to put out a lithium-ion battery fire. A fire extinguisher will not extinguish a lithium battery fire. If a battery catches fire, you cannot put it out. All you can do is try to control the fire and mitigate the possible damage associated with it. And we can talk about that again in a little bit more detail. One thing that I have added since our last discussion was a suggestion that you equip your shop with these heat protection gloves. These are readily available through industrial supply shops like McMaster Carr. One of the recommendations that we have is if a pack does begin to fail, that you actually take it and either remove it to the water-filled trash can or get it out of your store. But having these gloves handy will offset any danger that you might have relative to picking up a battery that's in a failure mode, so as to not burn yourself or your employee that's reacting to it. The protocols associated with this. This is our cardinal rule. This is the single most important thing you need to know, and that is never charge a lithium-ion battery unattended. And that applies not only to the shop, but also to e-bikes that you may have at home or customers that may have it. You never charge the battery unattended. If a battery fails, it usually fails during charging. And if it does go into a failure mode, there are very noticeable indications. It starts out slow. These things don't explode. A lot of people have the misconception that they go off like a bomb or a hand grenade. They do not. It usually initiates with a single cell. As that single cell is failing, it is generating heat, it's generating a lot of smoke, and it's noisy. So if there's somebody there to realize that something's going wrong, they can intervene. The whole point of the intervention is to try to check the propagation of the fire within the battery pack, and I will explain that in more detail in subsequent slides. Here again, if there's an attendant present, immediate action can be taken to minimize the damage. Do not charge bikes overnight. That is, I mean, if anybody's aware of what's been happening in the city of New York, these delivery e-bike drivers are bringing their e-bikes into their apartments, charging overnight. Unfortunately, those batteries can fail with catastrophic results. There have been numerous fires. I believe it's over 100 to this point, and there have been, at last count, I think 4 deaths associated with e-bike battery fires in apartments in New York City. Now that's a different usage environment than what we're currently talking about. Obviously, we're talking about the procedures in a shop, but the factor that's important to keep in mind is that you have many more than one e-bike battery in your shop at one time, which increases the possibility that this may happen. Again, it's minuscule chances that it will happen, but if it does, you need to be ready. These essentially are the storage and charging protocols. One, clearly, you should store all the battery packs in your store in the fire-resistant cabinet. That has generated some feedback to us. Some people have got problems with this recommendation, and I'll talk about those in a moment. You should store all new e-bike batteries in their original packaging in the cabinet. That necessitates, when the bike is received, that necessitates opening up the box, extracting the battery pack, and putting that into the cabinet. The questions that come up are, how many batteries can I fit in the cabinet? Will I have enough space in the cabinet to fit all the batteries in my shop, etc.? We'll address those in a minute. We recommend that you do not pre-charge new batteries. Wait until the bike is sold and you're preparing to deliver it to the customer. Don't pre-charge it, because all you're doing is you're loading more fuel into that pack, and if there is a problem, there's more fuel to burn off before it gets under control. So do not pre-charge batteries. Charge the battery as you're preparing to deliver the bike to the customer. As I say, the other point is that you want to store batteries from e-bikes that are brought in for service in the cabinet. If somebody brings in an e-bike, there's concerns that, one, is it an inexpensive bike with perhaps a questionable battery, or has it been abused? You don't know. So I would treat e-bike batteries that are brought in for service with a higher degree of caution, because they're not new, they've been used, they could have been abused, there could be factors present inside that pack that might result in a problem that you want to avoid. And then never charge a pack in the cabinet. As I said, the chances of a battery fire are increased when the battery is being charged. If you have one pack on the charger inside a cabinet full of batteries, it catches fire, you're going to lose the whole lot of them, and the fire is going to be a lot more intense than it would have been otherwise. So never charge a battery pack inside the cabinet. Only charge it on the battery charging rack. Relative to the additional protocols, here again, I'm repeating myself, only charge the batteries in the charging rack. Only use the charger type that's provided with the bike or with the battery. In other words, what I would recommend is obtaining extra chargers from your supplier so that you can dedicate one charger to your charging rack, zip tie it to the charging rack, use that exclusively for the batteries that it was intended for. Never charge a battery with a non-standard pack, never use a power supply, never use any device to charge a battery pack that wasn't supplied with that battery for its use. And then when the charger indicates that the battery is fully charged, take it off the charger, put it back in the cabinet, and wait, and then hopefully that will be shortly before you deliver the bike to the customer. In case of emergency, there are a couple of recommendations that we have in the event that this does occur. One, if the battery starts smoking, if it starts telling you it's in trouble and it's about to fail, and those signs are, as I alluded, smoking, making noise, showing melted plastic, if it smells, these things do a pretty good job of communicating the fact that they're in distress. If you can do so safely, place the battery pack in that water-filled trash can. I'll explain the rationale for that in a moment. If you can't do that, move the pack outside, away from any flammable materials. Let it burn out outside. That's the purpose of the extreme heat resistant gloves. You want to put those on, get that pack out of your shop as quickly as possible, because not only do they generate a lot of heat, they generate toxic smoke, and you certainly don't want toxic smoke filling up your retail environment. Clearly, this makes sense, most common sense. Dial 911, get the fire department there. Let the pros come in to help deal with the situation. They know what they're doing. They'll be able to react, again, hopefully offsetting any potential damage that may occur. If the battery is on the charging cart and you can't move it safely, for whatever reason, it's too far gone for you to pick it up with the gloves, unplug the chargers that are zip tied to the rack and wheel the rack outside. You may have noticed, I neglected to mention it, but you may have noticed that the rack that we're recommending has wheels on it. Store it near a door or an overhead if there's one available in your shop. If something goes bad, obviously, if you can't do anything else, you want to get the thing out of the shop so that the smoke doesn't permeate the environment and the heat doesn't damage anything else within the shop. If there are other batteries on the charging cart that are being charged that are not involved, get those off the cart. Get them away from that failing pack so that there can't be additional propagation of that fire to additional packs that are otherwise okay. If the remedial actions that are recommended above are not possible, evacuate the store. The poisonous gas or the toxic gas is harmful. Get your employees, get any customers, and get yourself out of the shop. Let the fire department deal with it. This is the section that I wanted to explain to you some of the feedback that we've gotten from the first webinar, where we presented these recommendations, not only for the procedures and protocols, but also the what to do in case of emergency issues. One of the most vehement disagreements that we got was that in a large store with many e-bikes in inventory, it's not practical to remove the battery pack from every bike in the shop in inventory and put it in that rack. There are two problems with it. One, it's a lot of work. And number two, how many packs can you fit in that container? In the cabinet, you may find that you need additional cabinets to handle all those batteries. We understand that that's a problem. We understand that it requires a lot of work. You know, the reality of the situation is that these things can fail without any intervention on their own. There are certain issues, defects, if you will, associated with lithium-ion cells. They're very rare, but they can occur. And if they do occur, and you've got a battery in a box with inventory, an additional 20 or 30 bikes in that storage area, there's a good chance you're going to lose them all, and it's going to be more difficult to fight for both the shop personnel as well as the fire department. So while we understand this is a problem, our recommendation is deal with it. Considering the consequences of a fire, especially one that's in a battery box in the bike box, it's cheap insurance. It's a little extra work, but it certainly will offset the potential damage associated with a fire that occurs inside a battery box, inside the bike box, inside your storage facility. So, again, our recommendation stands. This is the best thing to do. Now, there's some good news here, and that's the fact that, as I mentioned earlier, batteries will most often fail when they're on the charger. And if the battery's in the bike box, chances are it's not on the charger. It's not under stress. And it's been shipped from the manufacturer in a partially discharged condition. There are international regulations that say you can only ship a lithium-ion battery that's 40% of its full state of charge. So it's safer than it would be if it were on the charger, but it's not ultimately safe. It's not as safe as it can be. So again, our recommendation is get all the batteries in the cabinet. If you need more than one cabinet, buy more than one cabinet, because again, it's cheap insurance. What about e-bikes that are equipped with a battery housed in the down tube? This has gotten to be quite popular. Most ATBs, for example, e-ATB, or e-mountain bikes, I should say, are equipped with battery packs that are stored in the frame. Oftentimes, it's very difficult to remove those battery packs. It's it's a shop procedure to extract the pack. What do you do then? It's not practically feasible to remove packs from down tubes on a regular basis and then put them in when you want to demonstrate the bike. We understand that. It comes back to our Cardinal Rule again. If the battery is contained in the down tube, it's not easily removed. When you're charging it, put the bike in an open area away from flammable materials and charge it. Never charge it unattended. If anything happens, what you can do, if it starts giving off indications that the battery pack is in a failure mode, you can wheel the bike outside. It's not the ideal situation, much like the issue associated with batteries packed in boxes, but you can mitigate the situation somewhat by just using a little common sense, anticipating that if there's a problem, the problem is going to be offset by the fact that you've taken steps to isolate the pack from anything that is going to be affected by that fire. When storing bikes with battery packs in the down tube, when the shop's closed at night, you can't put the whole bike in the cabinet. Isolate the bike again in the same area where you're charging it, but not on the charger. Don't charge it overnight. Don't charge it unattended. Put it someplace that if something's going to fail, it'll fail by itself, in a relatively isolated area. This again is when the smoke detector comes in handy, because that will alert the fire department to the fact that something's going on. Again, the fact that it's not on a charger is going to reduce the chances that there's going to be a problem. It won't totally eliminate the chance, but it will reduce the chance. And, that is better than leaving it on a charger overnight adjacent to flammable materials or other inventory. The other issues that we've talked about internally, we understand that some shops are going to have a lot of batteries. Some shops are going to have big inventory. How many packs can you fit in a cabinet? And it's more than just a size constraint. I mean, obviously, there's only so much volume inside one of those cabinets. You can get a better cabinet, but there's a deeper problem associated with this, because each one of those packs represents fuel. Each one of those packs, if it's contained in an area like that and something goes wrong, you don't want more fuel than you absolutely need. So we're currently working with an independent test lab to find out what is the fire-resistant characteristics of these fire-resistant cabinets. It's certainly feasible that we could put so much fuel in there that if it did catch fire, it wouldn't be able to contain it. The containment would be breached at some point due to the veracity or the ferocity of the fire, if you will. So we're looking into that. The other thing that we're studying as well is we need to prove the effectiveness of our recommendation to toss the pack into a trash can full of water. The rationale behind doing that is the fact that once a cell cooks off, it won't stop. It will continue to burn until all the fuel is exhausted in that cell. So what we're recommending is that we, instead of trying to put out the cell that's burning, we interrupt its propagation, because if a cell is cooking off, it's in thermal runaway, it's adjacent to a number of other cells, and I have some photographs I can show you in a minute. Those other cells ultimately will heat up to the point where they'll cook off. So the idea behind putting the pack in a bucket of water is such that the water will cool the adjacent cells while the failing cell is burning itself out, and will hopefully stop the fire with only one cell involved. But we need to prove that. There's a couple of factors here that come into question. That's the fact that a battery pack, for all extents and purposes, is watertight. Now, that water tightness will be compromised by a cell that's in thermal runaway, because it will melt plastic quite quickly, and it will melt aluminum, and I've got photographs that will prove that. It will melt aluminum as well in a relatively short period of time. The idea here is that once that containment is breached, water will flood the compartment, cool the adjacent cells, and stop the propagation. That is the rationale behind this recommendation, but we need to prove it out. We need to actually test it. As I say, we're working with a certified test lab. We're currently in the process of designing they call it design of experiments, to make sure that the parameters that we're looking to validate are in fact realistic, and we're going to be doing testing to essentially certify these recommendations. As soon as those answers are available, we will certainly convey that to you. But for the time being, we still feel that this is a wise action to help check the propagation of a lithium-ion battery fire in your shop. This is the point where I wanted to go into a little bit more detail about lithium-ion battery technology in and of itself. These things are amazing devices when you consider the amount of energy that we can store and the amount of power that's available from those battery packs. One might wonder, how do you do that? Well, this is a little primer, and I won't go into too much detail, but I think this is insightful in terms of your understanding of what we're dealing with. This is a photograph of the 18650 cell. This is the foundation of lithium-ion battery packs for electric bicycles. These were originally used in Teslas. A Tesla contains 7,104 of these. A typical e-bike will have something less than 100. But this is a lithium-ion cell. Its dimensions are 65 millimeters long. It's 18 millimeters in diameter. That's where the 18650 comes from. I'm not sure why they tacked on that extra zero. Maybe it should be 1008 or 1865, but that's the size of the cell. It's slightly bigger than a AA cell, and that's what's built into the battery pack to power your e-bike. Its nominal voltage is 3.6 volts. All of the cylindrical battery cells that are currently used in electric vehicles have a nominal voltage of 3.6 volts. Capacities, however, can vary. Typically in an e-bike, you'll see a 2.8 hour capacity in that pack. There are cells available that currently go up to 3.5 amp hours per cell. They're more expensive, but obviously they contain more energy. You'll go farther with them, but your pack will cost more. And now there have been developments in actually larger cylindrical cell 18650s. The popular one right now, which is currently being used in Teslas, is the 21700. As that implies, it's 21 millimeters in diameter and 70 millimeters long, so it's a little bit bigger, but they put more energy into it than for an electric car. That's very convenient. An electric bike, we obviously have space constraints. We generally use the smaller cell, although some companies are working on integrating 21700 cells into their bikes. It's a common question is, well, if the voltage is 3.6 volts and the capacity is 2.8 amp hours, how do I power a 36 volt bike or a 48 volt bike? You have to assemble these batteries in a certain serial parallel matrix to achieve the voltage and capacity attributes necessary to service the application that you're designing it for. So essentially what we do is to get the required amp hours, the required capacity, we connect a number of cells in what's called a parallel string. This is where you go from positive to positive to positive to positive to positive on the electrodes of the battery, and then conversely negative, 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 etc. That multiplies the capacity. So in the example there, I talk about a 5-cell parallel string. So 5 cells wired in parallel. If it's a 2.8 amp hour cell, you'll achieve a battery string of 14 amp hours. That's still 3.6 volts because we haven't increased the voltage, but we have increased the capacity. To achieve the voltage requirements to drive the e-bike, we connect those parallel strings in series. A series connection is positive to negative, positive to negative, positive to negative, which then becomes the multiplier for the voltage. So in this example, if I have 10 cells or 10 parallel strings in series, the voltage obviously is multiplied by a factor of 10. So with that 3.6 nominal voltage cell, suddenly we have 36 volts. This is a typical battery pack in an electric bike. We call it a 10S5P. Jumped ahead here a little bit. Those connections are made by actually spot welding a stamped nickel plate in the proper geometry to accomplish that serial parallel interconnect. And then, as I say, we designate that pack then as a 10S5P. It's 5 parallel strings wired in series with 10 parallel strings, which would achieve the 36 volts, 14 amp hour pack. Now, for a 48 volt bike, which is gaining in more and more popularity, we'd put 14 cells in series or 14 parallel strings in series. That then achieves the higher voltage necessary for that particular configuration. And so that basically is how we achieve the required voltage and capacity necessary to make the e-bike that you're riding useful. Moving on, the other key component, absolutely critical component of a lithium-ion battery pack is the battery management system. There's an onboard computer in each one of the battery packs in the electric bikes that you sell. It's powered by a microprocessor. It's a programmable microprocessor. That microprocessor is programmed according to the requirements of the system that it's being integrated into. But its main function is to ensure that the battery pack is used in a safe and effective manner such that it's never overstressed and it's never damaged through use. And it does that by accomplishing a number of functions. One, it limits the discharge current. We talked about it before with the low power density lithium-ion batteries. Pulling too much current out of those batteries would cause a problem. The same is true for the high power density, energy density batteries. There is still a limit. And what we do with the battery management system is we program in that upper current limit. It's usually between 18 and 24 amps. In other words, the BMS will not allow you to pull more current than what it is capable of sustaining. So if you try to do that, it will limit the current output of the battery to ensure that it stays safe. It will also enforce what I call a low voltage cutoff, LVCO. You never want to over discharge a lithium-ion battery because in its over discharge state, a phenomena called dendritic cell growth can occur, which will compromise the reliability of the battery for the future and can initiate a fire by piercing the separator and causing a short circuit. So initially we limit the discharge current and we limit the amount of power that you can take out of the battery before it turns off. When you hit LVCO, the battery management system shuts down the bike and it won't give you any more power to power that bike. So when that LED on the state of charge indicator starts flashing, head home or to a charger. The other thing that it does relates to voltage. It limits the amount of current in recharging for the same reasons, just the same reason that you can't pull out too much amperage from the battery when you're using it. You can't put too much amperage back in while you're charging it. So LVCO the BMS manages that as well to see to it that you don't overstress the battery pack when it's being recharged. And it also ensures that you can't overcharge it. Generally speaking, in the case of a 36-volt battery, its fully charged condition is about 42 volts. When the battery management system sees that the battery pack has been charged to 42 volts, it turns it off. It's slightly higher, obviously, for a 48-volt battery. But the point is it will not allow you to charge it too fast, and it will not allow you to overcharge it. It controls those aspects of the battery's function. Another factor is called cell balancing. We talked about the parallel strings in the battery pack. The parallel strings represent one of the series elements that goes into the pack. If a parallel string is undercharged and the battery is used, that parallel string will be overstressed. So the battery management system measures on a real-time basis the state of charge for each parallel string, and it adjusts the charging protocols to make sure that each parallel string is within about, I think it's about a tenth of a volt. So you want all of those parallel strings to be at approximately the same voltage so as to not overstress a parallel string in service. And that's another function of the battery management system. It monitors and regulates pack temperature. The battery pack has got several thermistors built into the cell matrix that measure the cell temperatures. A hot battery is an unhappy battery. The way the BMS manages temperature is if a thermistor senses that the pack is getting too hot, it throttles the amperage output to download the stress on the pack. So if you're riding, if you're doing a hard ride, say on a mountain bike, and all of a sudden it seems like you're losing power, it's because your battery pack is getting too hot, and the battery management system is saying slow down, and it will make you slow down by limiting the amount of power that it can provide to the drive system. Battery management system also manages sleep, wake, and deep sleep functions of the battery pack. You're all probably aware that the battery pack will go to sleep if it's not used for a period of time. That's important because it limits the amount of parasitic discharge that's going on that will draw the battery charge down over time. Deep sleep is when it senses that the battery is so far in a discharge condition that it basically shuts it down, and special methods are required to turn it back on, because a fully discharged battery that continues to discharge will be a dangerous battery when you try to use it again. So it's another function that's managed by the BMS. There's a fuse integrated into the battery management system. If there's a short circuits to a lithium-ion battery are bad news. That a short circuit is an instantaneous rush of current. And we talked about current limitations. A short circuit will override that current limitation function of the battery management system, and it can result in a failure. So there's a fuse built into the battery management system to see that that doesn't happen. The really cool thing about the battery management system is the microprocessor records the entire service history of the bike. Every time the battery is charged, every time the bike's ridden, it collects quite a bit of data relative to that service. It measures the state of discharge, it measures the state of recharge once it's charged, it measures the ambient temperature that the pack was in during use. There's a wealth of information that's provided. There's a historical perspective on all the aspects of its interaction with the battery pack that can be downloaded for diagnostic functions. This is a great assist to a manufacturer. If a battery is abused such that it violates the warranty, by looking at the pack, you don't know that, but by connecting appropriate instrumentation to the bus in the battery pack, you can learn what the service life of this battery has been. And if it has been abused, you can either reject the warranty or advise the customer that he needs to replace the pack, because it is truly a minute by minute record of the operation that this has gone through. There's clearly enough memory in the pack, and that's accessible. I think I talk about, the service data and system diagnostics can be downloaded with a communications protocol, either CAN bus, which stands for Controller Area Network. That's the electronic communications protocol that your car uses. Obviously, automobiles nowadays have got more computers than you can imagine, and all of those computers talk to themselves via CAN bus. We used to use UART. UART stands for Universal Asynchronous Receiver and Transmitter. And essentially, it's the language that the electronic components use to talk to each other. In our particular case, we can extract the information relative to the battery's use, as well as potential problems, via an interface, via CAN or UART, to a computer that you can use to take a close look at what's going on in there. And that can either be done by Bluetooth, if the BMS has got a Bluetooth module on it, an NFC or near field communications functionality, or simply a hardwire that you connect. So this is truly an important element of a lithium-ion battery, and it obviously has a lot of important functions to perform. But I'm sitting here telling you how important it is to the BMS function in terms of ensuring a safe battery pack. And it truly is, because it prevents the pack from being abused to the extent that it can fail. But it cannot protect against the defective cell. This is the point that we want to make. When you consider the number of lithium-ion batteries that are produced over the years, it's unimaginable that some of those aren't defective. In fact, I ran some statistics. As of a couple of months ago, there were 627,350 Teslas sold, and each Tesla has 7,104 battery cells in it. So that's a total of 4,456,694,400 battery cells just in Teslas, not counting all the e-bikes and scooters and whatnot that are out there. So, even at the most stringent quality control methods, if you've got a 0.00001 failure rate on those cells that are produced, you can still have as many as 44,000 defective cells in the marketplace. Cell defects can take a number of forms. A contaminant on the separator. The separator is a very sophisticated material that's wound in that cylindrical battery that isolates the cathode from the anode. If that separator is pierced, or if it fails, if it's compromised by an inclusion or some sort of a foreign particle on there, if the separator fails, there's a direct short between the anode and the cathode. It can result in thermal runaway, which will start a fire. So in Teslas, the mitigating factor there is the fact that a Tesla battery pack is water cooled. Heat is the enemy of a lithium-ion battery. It's not practical to water cool e-bike battery pack. So the water cooling in a Tesla alleviates a lot of the stress on the battery pack because it takes away the heat very aggressively. That's not available to us in an electric bike. So a defect that might not manifest itself as a fire in a Tesla could cause an e-bike battery to fail. So this is the fundamental reason why we say take precautions, assume that you're going to have a fire, make sure that those precautions ensure that the consequences of that fire are thoroughly mitigated. until such time as we can get solid state batteries in the marketplace, at which time these issues will go away. And wait a second, what have I got here? Oh, I wanted to show you a photograph. This is a typical lithium-ion battery pack. This is a 10S5P 50-cell pack. This was used on a Fairly E-Flow e-bike. It was contained in the seat mast. You may have seen the Fairly bike that had the battery pack. It's a humongous seat post. The battery's contained therein. The point I wanted to make with this photograph is you can see how close these cells are together. If one of the cells in that pack fails, clearly there's a direct path for the heat to transit from the failing cell to its neighbor, causing the neighbor to cook off, causing its neighbor to cook off, et cetera, et cetera. This is what we want to interrupt. This is why we recommend that you toss that pack into a bucket of water, a trash can full of water. That will hopefully, and we'll prove it, cool the adjacent cells and prevent one cell from igniting a whole pack. I like to draw the analogy. If you have a gasoline fire that involves a pint of gasoline is a whole lot more desirable than having a gasoline fire that involves 15 gallons of gasoline. So what we're saying here is let's try to contain the fire to one or two cells, let them burn themselves out while the water medium is cooling the adjacent neighbors. This will be verified, this will be tested and proven, and we will report to you then. As I say, this is the basis for our recommendations, and that's what we're trying to say. That's what we're trying to get across. If these procedures, these protocols are implemented in your shop, if something bad does happen, and it's not out of the question that it will, this is an appropriate reaction to hopefully offset the potential damage that this can occur. Parting thoughts. Lithium-ion battery storage technologies are critically important in society today. I mean, they're enabling us to develop clean transportation methodologies. And that's so critically important in these days of climate change that we offer this. Unfortunately, given the state of the art today, certain characteristics associated with this chemistry, when coupled with improper design, fabrication, poor quality, or misuse, a fire can occur. And it's a bad fire. Once one of those cells goes off, you can't put it out, and it's a hot, smoky, dangerous fire. That's what we're trying to address with the solid state batteries in the future. Significant efforts are being placed according to this. I mean, I monitor the newsletters every day. There was a breakthrough at the University of Pennsylvania just today that was announced, whereby they figured out how to manufacture a solid state separator. This is the news that hopefully will result in manufacturing technologies that will produce these things and make them commercially available. But in the meantime, we have a liquid electrolyte in there that's flammable and can cause a problem. These realities and the supporting technologies render quality lithium-ion battery packs expensive. This is one of the issues that people have when they're looking at a bike. What happens when my battery reaches its end of life and I have to replace it? It's a big hit to the pocketbook. But just as we say, quality batteries are expensive, poor quality batteries are dangerous. I'm quite concerned that the pandemic has resulted in a significant increase in the popularity and volume of electric bikes sold. A lot of people are trying to jump on the bandwagon. They're bringing in very low cost electric bikes, considering that the battery pack is the single most expensive component on an electric bike. Where are you going to cut cost? If I want to bring in a bike and sell it for $1,000, what am I going to compromise? And unfortunately, in my opinion, it's the battery. Using poor quality cells, using improper battery management systems, using improperly battery management systems that have been improperly programmed can and will result in catastrophes. So we want you to always replace a battery for your customer with an original equipment battery obtained from the supplier of the bike. And we also want you to be very wary of low-cost e-bikes and replacement packs from third-party vendors. It doesn't happen a lot, but when it does happen, it's ugly. So those are the extent of my prepared comments. Are there any questions that I can answer?
We have a couple, yeah. So I'm just going to start reading them out.
Okay.
Do you have any information on the propensity of battery failures among batteries from major brands versus off-brand and non-branded batteries?
Anecdotal only at this point, and we've had internal discussions about how we can get better research on that question, because clearly I'd love to be able to say that the chances of this happening are 1 in 1,000. I can't say that from a knowledge base. Anecdotally, I know it's the case because I've seen low-cost batteries fail. It's a reality. My recommendation is if I advise clients that if you're going to develop an e-bike and you want a safe battery pack, source your cells either from Panasonic, LG, or Samsung. They, in my mind, produce the highest quality batteries. They're Korean or Japanese. As I alluded earlier in the conversation, one of the failure modalities of a lithium-ion battery is if the separator is contaminated during production. LG, Panasonic, and Samsung have the highest levels of quality control in their production facilities. The likelihood that one of their separators is going to be contaminated is low. I don't want to seem racist, and I don't want to cast aspersions, but generally speaking, I don't trust Chinese cells yet. The Chinese battery industry is still working on it. We're working with a Chinese battery manufacturer called Philion. I think Philion is going to be very close to having very safe, stable cells in the near term. But beyond that, I do recommend cells from the highest quality manufacturers that are available and avoiding cells that are less expensive or produced anywhere else. That said, I have a lot of confidence in Chinese battery pack manufacturers. The pack manufacturers, when they use cells from either the Japanese or Korean suppliers, produce excellent packs. Most of the clients that I work with source battery packs from Chinese pack assemblers using high quality cells, and we've not had a problem.
How can you tell if a charger and battery are properly matched? Most of the battery labels don't match the charger labels.
Usually, one method is most, and this is not foolproof. Most battery pack suppliers will supply a charger with a plug matched to their battery pack. There's a variety of different plug styles, and one way that you can not assure but be somewhat comfortable that you're getting the right charger with the battery. Probably the simplest thing to do is just make sure that you're getting the charger and the battery pack from the same supplier. All e-bikes are sold with the pack and the charger in the box. Just make sure that you don't separate those. One of the other issues associated with the logistics of inventory is making sure that you you bring the battery that was supplied with a given bike back to that specific bike when it's sold. Everything is serialized. There are serial numbers on the bikes, there are serial numbers on the battery packs. It's important to make sure that you're matching them up. Plus, there's a lot of different, it doesn't relate to the chargers, but it relates to the batteries. There's a number of different pack geometries that are incompatible with other brands. So, but the safest bet is to make sure that you're supplying the charger that came with the bike.
All right, the other questions we got came through as you were giving the presentation, and they were answered quickly afterwards. So here we go, one more.
Good.
Can you follow up with a seminar of what to tell customers when they're buying an electric bike? We don't want to scare them, but
Yes.
want to know the safest way.
The easiest thing to tell a customer, and we can do a webinar on this by itself, but the easiest thing to do is, number one, Cardinal Rule: don't charge it unattended. Don't plug the bike in the garage. Don't plug the charger into the battery in the bike in the garage and go to bed. I investigated a fire. One time I was brought in by the battery pack manufacturer to do a forensic analysis of a battery fire that happened in a house. And the customer had been complaining that the battery pack was acting weird. Nevertheless, he put the battery on his kitchen counter, plugged in the charger, and went to bed. He was woken by the smoke detector in the fire department that came to put out the fire. Don't charge it unattended. When you do charge it away from flammable materials. The easiest thing to do is charge it on the garage floor, away from the lawnmower gas can. Charge it, or charge it in the bike, but make sure the bike is not close to flammable materials. But don't charge it when you're not home. Don't charge it when you're in bed. Don't charge it when there's not somebody there to intervene if something happens.
Is there concern with using a standard fire cabinet versus one designed for batteries by companies like Cellblock?
I don't think so. And again, that's part of the questions that we're trying to answer with this involvement with a testing lab. I've talked to UL about this, and UL wants us to use explosion-proof cabinets, but they are expensive. And these batteries don't explode, they burn. What we need to do is we need to make sure that we need to determine how many packs can be in a cabinet such that if those packs fail, they don't overwhelm the protection capabilities of the cabinet itself. And that's another question that we're looking to answer. Clearly, the better the cabinet, the better the situation, but those things are expensive. I found in the literature cabinets that are supposedly explosion proof, designed to carry high capacity lithium ion batteries, and I don't think they're feasible or practical for an e-bike shop. But we may amend that answer once we get the results of this pending testing.
Is there any built-in protection if the wrong charger is used accidentally?
That's a very good question. One of the developments underway, and this has been talked about for years, we talked about the various communications protocols that are used in electronic systems. There's been a lot of discussion about integrating CAN capabilities into the charger, such that when the charger is plugged into the battery management system sees it and can certify it for use with that particular battery pack. That doesn't have wide distribution at this point. The good news is that the battery management system will control the inflow of energy from the charger such that it shouldn't be a problem, but it's just not good practice. As I mentioned earlier, one of the functions of the battery management system is to monitor charging, and the main attribute, if you will, of the charger is its charging amperage. In other words, it's designed to push so many amps into a battery pack, usually 3 to 3.5 amps over time. And most batteries are fine with that. If it's a higher amperage rated charger, the BMS will sense that higher amperage and it will shut it down. It will open a FET, a field effect transistor, and preclude charging. So that functionality is built into the battery management system, but I wouldn't rely on it in that sense. Always use a charger that's supplied with the battery pack.
Here we have a retailer who wrote in, we've been working on a plan to implement your recommendations. It's been super hard and cumbersome to the point where we're weighing the rare risk and the sizable change in the way we work. What do you say to those sitting on the sidelines?
That as I mentioned, that's some of the feedback that I've gotten is that there's no way we can pull the battery packs all the bikes we receive and put them in a cabinet. It's just a lot of work. I understand. The key term here is weigh the risk. I'll reiterate, it's extremely rare that this happens, but it does happen. So, it's kind of up to the shop. Our recommendation is to bite the bullet and do it. Hopefully, over time, as we learn more about this through the testing that we plan and the interaction with agencies such as Underwriters Labs and whatnot, we'll be able to amend our recommendations in this regard and such that the burden on the shop itself is eliminated or reduced anyway. But until such time, our recommendation is to put those packs in a safe place.
All right, that is all the questions that's come in now. If people have more questions, you can email them to info@nvda.com or Mike's email is right there on the screen. All right, thank you so much. Really, really informative. Hopefully we get more people that have questions so that we can get as many people using these recommendations as possible. So thank you for your time.
Just to reiterate, Rochelle, we're here on your behalf, and we're anxious and willing and hopefully qualified to help. So please don't hesitate to ask.
Thanks so much.
Thank you, Rochelle. Thank you, everybody.